So in this video, I'd like to solve the following example, and it says the corresponding Bode plot for the circuit is shown below, and we have to find the capacitances C1 and C2. So it's a relatively easy example because here we see that the non-inverting input of our amplifier is connected to the ground, and the voltage in the ground is 0. So if our non-inverting input is 0 here, then our inverting input is 0 as well. So these two voltages are equal. In that case, we can take our node voltage expression and let's say V1 minus, let's say this will be V0 equal to 0, V0 over 20 multiplied by 10 to the power of 3 plus 1 over j omega C1. So we see that at the output of the operational amplifier there is V0, so I chose a really not the best value for my voltage here. So let's say it will be a V ground. Okay, so V output at the output of the operational amplifier is also connected to the V ground. So we can express it as plus V output minus V ground. And here, please be careful. So it is a capacitance in parallel with resistance. So I'll write it in a rather bulky way for convenience and clarity. So here we have G omega C2 multiplied by our resistance, over 1 plus J omega C2 plus our resistance. So this is this circuit in parallel, okay? And all of that will be equal to 0. So if we simplify it real quick, it will become V input minus 0, which is still V input, over 20 multiplied by 10 to the power 3 plus 1 over j omega C1 equal to minus V0 over, let's say, 1 over g omega C2 multiplied by 400 multiplied by 10 to the power 3, and here we write this. Okay, so then it becomes rather simple because we can now take the relation of V0 over V1. And there is some really cumbersome calculation to it, but if you do through all this, if you go through all the steps, you will get something like this. So we may afterwards equate it to our expression of a network function that we can get from the Bode plot and find our values of capacitance 1 and capacitance 2. So here we can see that there was an increase, then there was assumably a pole because plus 20 dB then became a straight line, so something had to be subtracted from it. So thus I assume that this is nothing else but a pole, and after a straight line we again see a negative slope of minus 20 dB. So assumably our network function will be k multiplied by j omega, 1 plus j omega over 40, 1 plus j omega over 160. You may wonder, and this is a fair question, where does this term j omega come from? Well, as we remember, j omega is an increase, and 1 over j omega, on the contrary, is a decreasing slope. So since from our Bode plot we cannot really say where exactly this increase started from. We cannot say that this goes to 0, thus our 0 is equal to 0. No, we cannot usually say that. In cases when we don't know, we simply say that it is j omega. If we know indeed, then we say that, let's say in the case of these two, it is j omega over some kind of a value. Okay, so here we will apply our assumptions. So first assumption is that omega is less than 40. In that case, these two terms simplify, and we'll have h equal to k multiplied by j omega. In second assumption, if our omega is greater than 40 but is still less than 160, then this still simplifies to 0, but we have some change, and our function will be in the form of k multiplied by j omega. Remember that this term is not affected by any kind of simplification because it doesn't have neither 40 nor 160 in its denominator. So here we have j omega over 40, which leads to 40k. And if we take the gain of this of h in this specific situation, then we will have a constant value, right? And from our Bode plot, we can see that this region where our omega is greater than 40 but is still less than 160, our gain is equal to 26, which means that this whole thing is equal to 26. And if you go through some kind of calculation, you will find out that your k is actually 0.5. So if we further look down into our capacitance values, we can see that there is some kind of a relation as well. And don't worry about this negative sign. It simply means that it is an inverting circuit. So it doesn't really affect our capacitance values because this minus only has to do with, it doesn't have anything to do with the magnitude of our capacitances. So now we can calculate the value of our capacitance 1. And since we know that the numerator has to be equal to 0.5 multiplied by j omega 1, we can equate these two sides together. So we will have it equal to 400 multiplied by 10 to the power 3 multiplied by c1 j omega. So these two things simplify, and we have c1 equal to 1.25 10 multiplied by 10 to the power of minus 6. You can try finding the value of capacitance 2 by yourself, but I'll just give you a hint that it will be equal to 15.625 multiplied by 10 to the power of minus 8. So this is it. I hope you find it helpful.